Hello everybody, welcome to a session with calculus. Today we will be talking about the product rule. So last time we talked about the power rule for polynomials, and this time we're going to look at what happens when you try to take the derivative of a function that is a product of two other functions. So to begin with, let me just kind of throw an example out there so you can see what I'm talking about. Let's say that I want to take the derivative of y is equal to something that is simple as, like, say, x multiplied by x. Now, unfortunately, when you take the derivative of a function where you have a product, the derivative is not as simple as taking the derivative of the first multiplied by taking the derivative of the second. So then that way you can get the derivative. So here you see that if I take the derivative of x is equal to 1, derivative of x is equal to 1, so 1 times 1 is equal to 1. That right there doesn't work out, unfortunately, because if you know that x squared, if I that's the same thing as saying x times x is the same thing as x squared, and by the power rule from the last session, the derivative of that is going to be equal to 2x then, which is not the same thing. So the question is, well, then how do you actually take the derivative of a function where you have a product of two equations then? So that's where this guy comes in black right there. So it turns out that if you have a function where, like we said, is a product of two other functions, the derivative is supposed to be the first function multiplied by the derivative of the second, plus the second function multiplied by the derivative of the first. And what we're going to do right now is we're going to go ahead and prove the product rule. So if you are one of those people that like to see how the hot dogs are made, then go ahead and sit back for a little bit. But if not, you can go ahead and fast forward to the part on how to use the power rule. Okay, so let me first go ahead and erase all the stuff right here that I have, and let's go ahead and derive it now. So first what we'll do is we'll take our equation y, or function y, and use the formal definition of derivative then. So we have limit as h approaches towards 0 of f of x plus h times g of x plus h minus f of x times g of x, all divided by h. So that's just throwing it into the definition of derivative via the limit. So that's supposedly the derivative. Now, the part that's going to be a little bit tricky is that I'm going to take this fraction right here, and in terms of how do we actually get it, well, that's something that you might want to kind of think about then for yourself, because I don't want to give away all the secrets. I'm going to go ahead and take this fraction, and I'm going to do something to the numerator so we can actually see how it works out. First, we have f of x plus h times g of x plus h. That's the first part. And then I am going to add and subtract something. And that something, again, I'm going to leave it to you guys to figure out like where that actually comes from. That something is going to be minus f of x multiplied by g of x plus h, and then plus f of x multiplied by g of x plus h. So basically balancing out the equation, because I'm just adding, subtracting the same thing. And then we also have that last part, which is going to be minus f of x multiplied by g of x. So in essence, what I did was I basically kind of like quote unquote completed the square, because I introduced a term and I subtract a term. Now, what we'll do is we'll look at the first half of the numerator, and you'll notice that they both have g of x in common. So what I can do is I can actually go ahead and factor that out then. And similarly, for the third and the fourth term, we have f of x in common, so I can factor that out. So let's just see what that gets us then. So going back to what we have, limit as h approaches towards 0, factoring out the g of x plus h part from both of those terms. So g of x plus h factored out. Then we have f of x plus h on the top minus f of x on the top for the second part. And then all that is going to be over h. Now that's the first and second term broken up. Then for the second part, we have plus the limit as h approaches towards 0. Then we have f of x factored out. And what we have now is going to be a g of x plus h on the top minus g of x. And all that is going to be divided by h. So I kind of like did two steps right there. I took the fraction and broke it into two parts. That's number one. And then number two is I factor out the things that they have in common. Now, at this point, you might be able to see it a little bit further, and hopefully you do see this part. You'll notice that the first piece, there is a portion of it that looks like the definition of derivative. And what I'm referring to is this guy that's over here. And in the second piece, there's also a part that looks like a definition of derivative, and that's referring to this guy over here. Oops, I think I circled a little bit too much. Whoa, killed everything error, so we're gonna be careful about that. Let me go ahead and rewrite this guy over here. We factor out a f of x, actually, looks like, and then we have all of this on the bottom. Okay, good, so everything's still saved. So the next step, now let's go ahead and write it all out. The limit as h approaches towards 0 of g of x plus h, and then multiply by the limit as h approaches towards 0 of f of x plus h minus f of x, all divided by h. So you'll notice what I'm doing next is I'm basically going to break the limits into, again, two separate parts, because if you have, there is a limit law that we learned a while back where it says that if you have two functions, you can apply the limit to one part, multiply by the limit of the other part, so long as both functions are supposedly continuous. Then for the second part, we'll do the same thing. Now this second part, we're going to go ahead and do something a little bit different. We're going to go ahead and factor out, or actually put on the outside, just the f of x. And then we have the limit as h approaches towards 0 of g of x plus h minus g of x all over h. And I can actually pull that out of the limit problem, because keep in mind that the variable x has nothing to do with the variable h. So that's why we can take it outside of the limit. Now let's go ahead and finish it up. The first part is going to be limit as h approaches towards 0 for g of x plus h. That is really just plain old g of x. The second part, now that, what we said earlier, that's the definition of derivative, the formal definition of derivative for f of x. So that's going to be f prime of x. Then plus the third part, f of x is just f of x, multiplied by the fourth part, which is the formal definition of derivative for g of x. So that's going to be g prime of x, and there you go. That's going to be our derivation of the product rule then. Okay. So this method, I think you should be able to see in some of the textbooks, not a lot of them, maybe some of the older ones. Now, there are probably like 4 or 5 different ways to do it, so you pick the one that makes sense to you. What we'll do is we can look at the alternate derivation, and again, if this is if the derivation thing is not exactly your cup of tea, you can go ahead and fast forward to the next part as to like how to actually do the product rule, and I'll give you a few examples. So another variation, and this one I kind of like because I ran into this maybe about 4 or 5 years ago, and I've never actually seen it in a textbook. So this is actually kind of neat for me. So here we say that the alternate derivation for any function y is equal to f of x, or y is equal to p of x actually. So let me kind of sneak that in there, okay? The tangent line at any point at x equals to a is equal to y minus p of a, is equal to the p prime of a, and then multiplied by x minus a. So that is right there, the equation of the tangent line for any function p of x at x equals to a. And hopefully that does look somewhat familiar to you because you've done it quite a few times already in the last maybe like 2 or 3 sections, okay? So if you find a derivative, you can use the point slope form, and then that's where this came from. Now, we can technically take this and go a little bit further with it, and here's what I'm going to do. I'm going to go ahead and solve for y in this case then, okay? So here we have now y is equal to p prime of a multiplied by x minus a, and then plus p of a. So that's just moving the p of a over. And this right here, this is what is known as the first degree Taylor polynomial, and we'll discuss what a Taylor polynomial is in the second semester. But for right now, this is basically still the equation of the tangent line, but also known as the first degree Taylor polynomial, okay? So the reason why this is actually essential is that if you think about how a curve and a tangent line work, we can say the following, or hopefully you can kind of agree with me here. Let's say that here in the picture on the right hand side, you can see a curve and you can see a tangent line. If I manage to just kind of like magnify within a certain, I guess a rectangle, you should be able to see in that rectangle, or in that small little window, that the curve is going to be very similar, if not almost identical, to the tangent line. Okay, so let me repeat it again. For a very, very small window, right, for a very small window, if we magnify that window, we can see that the curve and the tangent line are pretty much almost identical. So here, if you kind of keep blowing it up, you can see that the tangent line is almost the same as the curve then. So for local value of x is equal to a, we can say that the tangent line is the same thing as the curve. Okay, so for a very localized value of x is equal to a, the tangent line is the same as the curve itself. So let's go ahead and try that then. So what we'll do is we'll go ahead and say that we're going to go ahead and use this, utilize this over here. First, y is supposed to be a function of x multiplied, y is supposed to be f of x multiplied by g of x. I'm going to replace each one of those equations with their tangent line equation because, again, for a very, very minimal, for a small window, the tangent line and the curve are actually one and the same, okay? So let's see, y is going to be equal to f of x. That gets replaced by this Taylor equation that we just came up with. That's going to say the following then. F prime of a multiplied by x minus a, okay, and then plus f of a. Okay, so that's replacing it with the tangent line. Multiplied by g of x, that's going to get replaced by its tangent line also at x equals to a. So g prime of a multiplied by x minus a, and then we have plus g of a. Okay, we're going to go ahead and carry out the algebra here. And we're going to go ahead and multiply everything out then. So y is still equal to, if I use FOIL, we're going to get the following. F prime of a multiplied by g prime of a multiplied by x minus a quantity squared. Then we have plus f of a multiplied by g prime of a multiplied by x minus a. Then we also have g of a multiplied by f prime of a multiplied by x minus a. And it looks like I'm running a little bit out of space, so let me go ahead and erase some of this over here. And there's one more piece to that FOIL, and that's going to be the following. And it looks like it's going to be plus f of a times g of a. Okay, so bear with me, we're almost done with this. Okay. This part is another part that's a little tricky. As x approaches towards a, okay, because as x approaches towards a, we got to think about what happens to some of these terms, okay? As x approaches towards a, because remember, we want to get as close as possible to the point of tangency, I'm claiming that this term right here, that is going to go to 0, okay? And let me kind of write that out. As x is approaching towards a, because we want to make sure that since we're saying that the tangent line is the same as the curve, we have to make sure that the value of x is closest possible to a as possible. The reason why this term right here is going to vanish into 0 is because of this guy right here, the x minus a quantity squared. You take a very, very small number, right? And when I say a very small number, I'm basically saying a number that's between 0 and 1, and that's very, very close to 0. You take that number and you square it, the result is that you're going to get something just so close to 0 that we can say that it's basically negligible, while the rest of this is still going to be still there, okay? So as x approaches towards a, this whole first term is going to go to 0. Yes, I understand that we have x minus a over here, that's squared. And then we also have x minus a over here on this term. Well, why don't they go to 0 and why don't they go to 0? Well, the reason is, again, remember, these numbers that is represented by x minus a quantity squared, as this is getting closer and closer to 0, this guy, because it's squared, it's getting closer and closer to 0 a lot faster than the other two. Okay, so again, that's the reason why that is going to be banished off. So looking at what we have left, well, that's going to be only 3 terms left. Now, keep on going. If you buy everything that we have so far, we're almost done, actually. If you look at now the first 2 terms over here, okay, if you look at the first 2 terms over here, they both have x minus a in common. So I'm going to go ahead and factor that out. So factoring out the x minus a in common, we're going to have the following. F of a times g prime of a plus g of a multiplied by f prime of a. And all of that is now multiplied by x minus a. Then we also have plus f of a multiplied by g of a. Okay. And this part, if you can kind of, work for me here, think back now to the form of the Taylor polynomial that we had earlier, how we said that this is the first degree Taylor polynomial. If you look at it carefully, that's exactly what we have, okay? That's exactly what we have. We have the x minus a part, right? We have the p of a part. Now that's supposed to be this whole thing, remember, because p of a, right, the p of x is supposed to be equal to the function of the two multiplied together, okay? So that is supposed to be my p of a then. Well, this part is supposed to be x minus a, which matches with my equation. So this part right here that's multiplied to it, according to my first degree Taylor polynomial, that's supposed to be p prime of a. So that's this guy, and all of that is still equal to y. And right there's your proof once again for the derivative of the product rule. P prime of a, which is supposed to be where p of x is equal to f of x times g of x. The derivative at x equals to a is going to be this piece right here, okay? So a little bit hard to swallow. So, you can feel free to go back and rewind this and look at it over and let it sink in a little bit, because it took me a while to understand it also, okay? Okay, now we are also going to look at one other rule. This one is called the quotient rule. So meaning, what if your equation or what if your function is supposed to be a quotient, a ratio of two functions then? Okay, so if y is equal to f of x divided by g of x, then the derivative is equal to what? Well, I wrote it out what it's supposed to be equal to. So next part, we're going to go ahead and derive it. And feel free, if you feel like at this point you get a grasp as to how we derive this, I definitely recommend that you maybe take a pause of this video and try to do it yourself. And then afterward, let's see if we can come up with the same answer. So here, let me go ahead and get this part set up. According to the definition of derivative, first of all, we say let y equal to basically what we said, which is a ratio of two functions. Okay, we're going to use the formal definition of derivative. So limit as h approaches towards 0 of f of x plus h divided by g of x plus h minus f of x divided by g of x, all divided by h. Now, we're going to go ahead and clean this up a little bit. And again, feel free at any time, if you feel like you know where to go, pause the video, and I encourage you to try to derive this on your own. We're going to say multiply both top and bottom by g of x plus h times g of x. And the reason for that one is we're trying to clean up this rational equation over here that is just kind of like nasty because it's a fraction within a fraction. So it's just kind of like basic algebra cleanup. So let's go ahead and do that then, okay? I'm going to multiply both top and bottom by g of x plus h times g of x. And what we'll get is now the following. Limit as h approaches towards 0. And let me go ahead and actually kind of write that over here so it's a little bit easier to see, okay? So we're going to go ahead and get rid of this part right here and write out what we just said. We're going to multiply this. Right there with a blue this time, okay? Multiply this by g of x plus h, multiplied by g of x plus h. So if we do that, we're now going to get the following then. The first term, the g of x plus h cancels out. So now that gives you f of x plus h multiplied by g of x. Then the second term, that is going to be the g of x cancels out. So that's f of x times g of x plus h. And all that is divided by h times g of x plus h multiplied by g of x. Okay, so this one, the proof of it is kind of like the first one where it's a little bit tricky. And what we're going to do is we're going to add and subtract a certain amount. So then that way we can see the formal definition of derivative. Now, in terms of what that's going to be, here is what we're going to do. Okay, so the first part, we are going to say f of x plus h times g of x, okay? And then let's see if I can kind of wiggle out of this one. So let's see, I'm going to put in blue right here. How about minus f of x plus h, okay? And multiply by g of x. And then we have plus for the other part, f of x plus h times g of x, and then we have minus f of x times g of x, x plus h, all divided by x, all divided by that denominator. Okay, so I'll go ahead and change that part in a little bit. So here's h, here's g of x plus h, and then here is g of x. So let me erase a little bit over here on the right because that's not what I added, and I want to make sure everything is color coordinated because, you know, little part of me is a little OCD, unfortunately. So let's go ahead and put that in red. So the red, that's supposed to be minus f of x times g of x plus h. Okay. Okay. So the first and the second term, again, we're going to take out what they have in common. So giving myself a little bit more space over here. So limit as h approaches towards 0, we're going to take out the g of x that they have in common. Then what we have left between the first and second term is supposed to be, oh, actually, you know what? I think we are kind of like in trouble right here because that's actually the same thing as the first term. So, oh, I think I know what I did wrong. Okay, so pardon my mistake right here. Let me instead do the following over here. Let me multiply by f of x times g of x. Okay, and let me multiply over here f of x times g of x. I think that'll actually fix it. So there's that part, and then there's that part right there. Okay, sorry, I apologize for that. Okay, so as I was saying, we're going to go ahead and take out from the first term and the second term right here. And again, we'll just go ahead and kind of highlight that. We have these two guys, okay, take out what they have in common. And then for the other one, we have, let's see, these two guys, we're going to take out what they have in common. So the first two terms, what they have in common is supposed to be the g of x, and what's left is supposed to be now the following here. And let's see if I can write that out. That is f of x plus h minus f of x. Ah, there we go. That works out because you can now kind of like start to see the definition of derivative that we're looking for. And all this, right, and we're going to break it up just like last time, divided by h multiplied by g of x plus h times g of x, and then plus for the second part, we're going to go ahead and say limit as h approaches towards 0, breaking the limits, factor out what they have in common, and that's going to be f of x. Okay, and I think we're going to also have g of x minus g of x plus h, and all divided by, again, h times g of x plus h, and then times g of x then. Okay, we're almost there. Let's see, the first guy, okay, the first guy right here, we can actually have the g of x cancels out from both top and bottom, so that's actually kind of nice. So let's see, if we go ahead and cancel that, cancel here and cancel here, now we are going to start organize some of the terms. So limit as h approaches towards 0, I am going to have 1 over g of x plus h on the bottom, multiply by limit as h approaches towards 0 of f of x plus h minus f of x, all divided by h, yeah, right there. And so we're starting to slowly build the formal definition of derivative then, as we can see. Then for the second part, same thing. I'm going to go ahead and take out the f of x. And what we have now is going to be the following over here. The limit as h approaches towards 0, the part that we need for the derivative of g is supposed to be, now this part is reversed. You'll notice that g of x plus h is second and g of x is going to be first. So we can actually remedy that by making the negative of it. So now we have g of x plus h minus g of x, okay? And then all that divided by h. And then we also have all the other stuff over here too. So what's there? That's going to be limit as h approaches towards 0 of 1 over g of x plus h times g of x then. Okay. So let's see. The first part, as h approaches towards 0, the first part is going to be 1 over g of x. The second part, that is going to be our formal definition of derivative. So that's going to be f prime of x. And I'm going to put that up on top so it gets a little bit easier to simplify. The second part, we have f of x. Okay, so that's kind of like a numerator. And then we also have negative g of x. Okay, so multiply by negative g prime of x. And we have in the denominator g of x multiplied by g of x. So this tells me that in order for me to combine the two equations together into one single fraction, I need a common denominator. So over here on the first part, we're going to go ahead and multiply g of x to both top and bottom then, okay? So that is going to be how we're going to combine it. And let's see what we get now. So that's going to be g of x multiplied by f prime of x. And then that negative, we'll just go ahead and take it out in the very front right there, minus f of x multiplied by g prime of x, all divided by g of x quantity squared. And there you go. That's your derivation then. Okay, so thank you so much for sitting through that with me. If you like that part, well, then maybe in the future you can derive more of the stuff with me then, okay? Okay, but here you go. Here are some of the sample problems, and let's see how they actually work out then with the product rule and the quotient rule. So in the first part, we have a product of two equations, and I would like to apply, in this case, probably the power rule, the quotient, the product rule for this, okay? So here, since it's the first time we're seeing it, let's go ahead and kind of like isolate some of these. So we're going to go ahead and say that the first function is going to be f, and the second function is going to be g, okay? Now, so that tells me that y, my equation, is going to be f times g. According to my product rule, is going to be g multiplied by the derivative of f plus f multiplied by the derivative of g. So hopefully that's kind of like easy to memorize. The first few times when you first see it, if you're not kind of sure, here's what I like to do. I like to write both of the equations here. So here's f, which is supposed to be x cubed plus 4x, and then g, which is supposed to be e to the x. I'm also going to write their derivative on the bottom. So that's going to be 3x squared plus 4 according to the power rule. And the derivative of g, which is e to the x, is supposed to be itself, which is e to the x. Okay. Now we're going to go ahead and now apply to the product rule once again to this. And if you look at the equation, all you're really doing is just cross multiplying them and adding them together. So again, that's the reason why I like to write it out so you can see everything. Do you necessarily have to do this every single time? The answer is no, but if it helps you to see it, it's probably preferred to. So here it is. Let's see, the derivative is going to be the first equation, which is going to be 3x squared plus 4 multiplied by g of x, which is e to the x, and then plus for the first part is going to be x cubed plus 4 multiplied by the derivative of g, which is supposed to be e to the x. So again, just to kind of help you see it once again, so that's f prime multiplied by g, and then plus the first part, which is f multiplied by g prime. Okay. And technically we have the derivative, so that's going to be nice. But what usually is something that we're going to have to do for the future is that we're going to have to take this and factor it, because we actually need to be able to do something with the derivative later on. So we're going to go ahead and finally factor out what they have in common. So that's e to the x. And what's left is going to be 3x squared plus 4, and then plus x cubed plus 4x. And yeah, we'll just go ahead and leave it at that point then, okay? So that right there is going to be our derivative. So this time, let's go ahead and use the quotient rule then. So what we'll do is we'll do exactly the same thing. I want to take the derivative of 9x to the 7th divided by x squared plus 1. So again, just like before, what we'll do is we'll write out each equation. The numerator we'll call f is supposed to be 9x to the 7th. Its derivative is going to be 63 times x to the 6th power by the power rule. Then we have g, which is supposed to be x squared plus 1. G prime is going to be equal to 2x. So let's go ahead and write it out. Okay, so the derivative, again, if you just haven't seen it yet, or you're not too familiar with it, is supposed to be the following. Y, if that's equal to f divided by g, then y prime is supposed to be g f prime minus f g prime, all divided by g squared. And at this point, it's literally just, again, kind of like cross multiplying, and then you're going to subtract, and then that's pretty much it. But the order actually does matter, unlike the product rule right here, so be very careful. So the derivative, according to what we have, it's going to be g, which is going to be x squared plus 1 multiplied by the derivative of the top, which is going to be 63x to the 6th, and then minus the first equation, the numerator's equation, 9x to the 7th, multiplied by the derivative of the bottom, which is going to be 2x, and all that is divided by, in parentheses, x squared plus 1 quantity squared. And again, just like the previous problem, if possible, we're going to go ahead and factor this because we want to keep everything in factor form for future references. What I'm noticing is that they both on top have x in common, And actually, it looks like you can take out x to the 6, and in addition to that, a 9 then. So let's go ahead and factor that out then. So we're going to go ahead and take out 9x to the 6. And if we do, let's see, the front term, we're going to have the x squared plus 1 multiplied by, looks like it's going to be 7 multiplied by x then. Oh, sorry, multiplied by nothing, just plain old 7. And then we have minus for the second part, the 9 taken out, that's nothing left. X to the 8th is what we have. We take out x to the 6th, so that's going to be minus x squared. And then we have all divided by x squared plus 1 quantity squared. And we'll just clean it up one last time. So final answer is 9 times x to the 6th. And on top, looks like we have 7x squared minus x squared, so that's a total of 6x squared, and then plus 7. And all divided by x squared plus 1 quantity squared. So there you go. That's going to be a derivative of the second equation using the quotient rule then. And here's a final example. Find the equation of the tangent line, f of x is equal to that equation at x equals to 3. So if I want to find the equation of the tangent line, what that means is we're going to have to solve for the derivative at x equals to 3, plug it in, and then afterward use the point slope form just as we've been doing so far. So let's go ahead and see if we can do that then. So once again, let's go ahead and write it out. So here is f prime of x, right? So the derivative, this is you're using the quotient rule. The quotient rule says it's going to be the bottom equation multiplied by the derivative of the top equation, and then minus the top equation multiplied by the derivative of the bottom equation. And again, do I have to necessarily write it out like that? The answer is no, but I like for you guys to be able to see everything. So that's why I'm just kind of like taking my slow time in this case then. Okay, once you get used to it, then it goes a lot faster. So cleaning that up. So let's see, x minus 1, that's just x minus 1. The derivative of x plus 1, that's really just equal to 1. Minus x plus 1 multiplied by the derivative of x minus 1, that's also equal to 1. All divided by x minus 1 quantity squared. So keep trimming it a little bit more. So we have x minus 1 minus x minus 1, because remember here you have to distribute the negative over here, so be very careful about that. So it looks like on the numerator, the x's are going to cancel out. You have negative 1 times minus 1, so that's going to be equal to negative 2, all divided by x minus 1 squared. So that's going to be our derivative. And here's another reason why you also want to clean up your derivative equation. It's so that when you have to plug it in the value of x, it's going to be a nice and clean, simple equation instead of something that's really, really messy. Here, we're trying to solve for f prime of 3. So then that means we're going to have to plug in x is equal to 3 into that equation. And that's what that notation stands for, plugging in x is equal to 3. So if we do, we're going to get negative 2 divided by 3 goes in there. We're going to get 2 squared. So it looks like the derivative is going to be equal to negative 1/2 then. Okay. So hopefully I didn't make any mistakes, or that's embarrassing because, I do make a lot of mistakes sometimes. All right, so that's going to be our derivative, which is supposed to be the slope of the tangent then. Okay, so that's the slope of the tangent line at x equals to 3. We have the slope. We kind of have the point because we know what x is, but we need to figure out what y is. So in addition to that, we're going to have to solve for what's f of 3 by going back to the original equation and plugging it in. So f of 3 looks like it's going to be 4 divided by 2, so it's going to be equal to 2 then. Okay, so now we have everything. We have the slope, we have the coordinate, so we should have the equation of the tangent line. So final answer is going to be y minus 2 is equal to negative 1/2 multiplied by x minus 3. And I really always prefer to leave my answer in point slope form if possible for the equation of the tangent line, because it's a little bit more flexible in terms of what we can do with it a little bit later on. Okay, so you don't necessarily have to put it into the first degree Taylor. Yeah, you can just go ahead and plug it in as is. All right, well, thank you so much for watching, and please like this video if you like it. And again, I will see you next time then. Okay.